Okay, now suppose Q is a real symmetric positive definite matrix, n by n matrix, given an arbitrary set of linear independent vectors, P0 through P n minus 1, so there are n of them in Rn, then use the Gram-Schmidt procedure to generate a set of vectors, d0 to dn minus 1 using these steps. So d0 is just the p0, and dk plus 1 is modified from the pk plus 1 by subtracting this term. Okay, so this is the Gram-Schmidt procedure. And now the question is to show that the sequence of the vectors d0, d1 through dn minus 1 are Q conjugate. Well, this is just need to show that for each pair of these d vectors, the Q inner product of them is 0. Okay, so to prove this, we use induction. So we first show that d0, d1 are Q conjugate or Q orthogonal, and then assuming that d0 through some dk are Q conjugate, and then we show that the dk plus 1 is Q conjugate to every earlier ones. Okay, every of the early one. Okay, so to prove this by induction, as I said, we need to show this is equal to 0. So to show that this is 0 is straightforward, because d1 by the definition here is just the p1 minus this thing, and then we need to show that the inner product of this, or Q inner product of this with the d0 should be 0. Okay, we just plug in and break the parentheses, and then we see that this becomes this. Okay, the difference of these two, but these two canceled, and you see that everything canceled out, and you just have 0. So this shows the initial of the induction is correct, and then assume that decays. So I should say that d1, d0, d1 through decay are Q orthogonal or Q conjugate. So assuming that, so now just this is a little bit weaker. So what I should say here is that d naught, suppose these are Q conjugate, then we need to show that ddk plus 1 is Q conjugated with every one of them. Okay, every one from d0 to dk. Well, we just need to check that. We just plug in the formula for the dk plus 1. It becomes this. So just call this formula here, and reuse it here, and I break the parentheses already. So it becomes this times the qdj, just here, and also this times qdj. And again, they just need to show that. Well, the reason why I want to have one of this, I'm supposed to have the sum of the ji from 1 to k, or 0 to k. But I only have one term left, because the qj's, q0 to qk, sorry, d0 to dk, they are q orthogonal, right? They're q conjugate. So when I multiply this thing to q, say q dj, there is only one of these terms in the sum that is non-zero, because that's only the dj term is non-zero left. Okay, so that's why I only have this one here left. But now you can realize that again, these two canceled, and also this canceled with that, so we get 0. That's why we have the Q conjugacy for the dk plus 1 with all the previous d's. Okay, then this finished the induction.